the aspect ratio means if it is like 0.81 or greater than that, then it breaks down very quickly, and during that breaking down means it will have some kind of instability. So even a single vortex will form such thing, but two vortex just accelerate them and form several small rings. So this experiment was first created by Professor T.T. Lim in National University of Singapore, and I had an opportunity to spend 1 year with them. So, but that is recreated now because this experiment needs lots of precision to generate this two vortexing exactly similar to get these structures. So it is all due to vorticity dynamics. These are all water in water, so there is no question of surface tension. The two vortex ring that is coming, they are also the same water fluid. Only thing is color has been mixed into two different color to see those vorticity thing, how they reorganize themselves. And these vortices are everywhere in the fluid dynamics, so you will see many places. Okay. Okay.
Okay, thank you. So I'll now get started with the regular class. So, all right. So we'll continue with our discussion on how we model hovering helicopter using the simplest possible models, that is based of actuator disk theory or momentum theory. And like we discussed, this theory actually is very old. I mean, it was originally developed for marine propellers. It was then adapted for helicopters, especially the helicopter in forward flight, because propeller theory for a marine propeller or a helicopter rotor or anything doesn't change. It remains the same. But when you have to use it for forward flight, which we won't be doing in this current course, then I mean it requires some modification, and it was done by Glauert and some other people. So guy called Glauert, I mean, I think he applied it in 1930s sometime. Yeah. All right, so that is our model of the problem. You would have drawn this diagram in the last class. Yeah. And like we discussed, we are going to make use of the basic fundamental laws: conservation of mass, momentum, and energy. So let me connect my So we start with the basic conservation of mass equation. Which is given here. So this is the integral version of the what we call the continuity equation in aerospace domain. So the whole equation says that, I mean, mass flow into the control volume must equal the mass flow out of the control volume. So that is what this equation says, that there is no new mass getting generated inside the control volume. There is mass flow happening, but there is no mass generation as such, or mass consumption. So there is no mass added or removed. What is coming in has to go out. Then the momentum conservation. So again, if you look at the integral form of the momentum conservation equation, so this is sort of the equivalent form of your Newton's law, if you can imagine, yeah, because that also talks about momentum conservation. So you have F equals to integral over the control volume P ds plus double integral rho V dot ds V. That is time rate of change of momentum across the surface S. And what happens? So there are these two terms, and now in this problem scenario, like I mentioned earlier, even though the actual problem, the physical problem talks about these helical vortices getting set like this, we actually have idealized that problem with nice streamlined continuous flow like this. So we have assumed that it's the quasi one-dimensional flow, and therefore this equation will get simplified, and this term also will drop out because the pressure all around the control volume is exactly same. So the whole control volume has been set up in a manner that static pressure everywhere is same P. Therefore, this integral goes to 0. But the other term will remain, and we'll see the simplified version of that in a moment. And finally, the conservation of energy, where the work done on the fluid is given as a change in kinetic energy of the fluid, which is half double integral rho v dot ds and mod v square, where v is the velocity vector and ds is your area vector. So now these are the three key equations in the integral form. So conservation of mass, conservation of momentum, and conservation of energy. So what we do is that we make some simplifying assumptions about these equations. And what are these assumptions? All right. So, well, we assume to begin with that the fluid is incompressible. Now, the question is this valid? Because Professor Das taught you, I mean, just a short while back, I mean, just few days back probably, that, I mean, anything where, I mean, my Mach number exceeds 0.3, I have to take flow as compressible. Even sometimes, I mean, for scenarios with lower Mach numbers also, you may have to consider compressible flow, especially when there is piston movement and those kind of things happening. But here for helicopters, if I try to see what is the typical Mach number at the tip of the helicopter rotor blade, and it's mostly sort of fixed for most of the helicopters, and the Mach number, I'll give you an example. For example, the Black Hawk helicopter. So the tip Mach number, M tip, would be equal to 0.65 in hovering flight. So if it is of the order of 0.6. So clearly the idea that, I mean, I should assume it to be incompressible is not physically correct, but nevertheless, this is a model, and to make our lives easier, we are assuming this. Okay. So we are aware that it is probably not very true, but we'll nevertheless make this assumption.
Just add, Abhishek, when we see the tip Mach number as 0.6 or 0.65, because it is a rotating thing, so near the root chord or mid chord, it will be much less than
right. So I was just about to come to that. So what happens? See, the blade is actually like this, and it's stationed about a point like this, and the entire blade is spinning with an angular speed omega radians per second. So every point on the blade actually would see a different velocity. While for a fixed wing, if I have an airplane, this is my wing, the velocity is actually constant everywhere, doesn't change. So my Mach number at the tip and the root are going to be same, more or less. Although I have drawn it here slightly swept wing without having an intention for that. So assume a rectangular wing, I mean, everything will be same everywhere. Even for a swept wing, I mean, it will be same as long as the sweep doesn't change. But here my speed is changing everywhere. So speed, if you see, the velocity at which it is coming would be a function of omega times y at a location y. So if this is distance y, it will be like that. So therefore, everywhere the Mach number is actually changing. So that is the first assumption. Second assumption is the flow is steady. And for helicopters, hovering condition is the steadiest possible scenario that we can have. Otherwise, I mean, all the time, I mean, there is a lot of unsteadiness. There is a lot of periodicity, but unsteadiness. Third very strong assumption is that there are no viscous effects. All right. There is no swirl. And that is why, I mean, we have said that, I mean, the flow is actually nice and straight. But we know that, I mean, the tip vortices are actually circling around the whole control volume. Again, this is there to make it simple. And finally, the quasi one-dimensional. That is, my fluid properties change only with the distance above or below the rotor, and there is no change along the plane of the rotor. So if this is my helicopter rotor and it's hovering like this, so there is no change in this direction. All right. So no changes along the in-plane direction. Changes would only be experienced above and below the rotor. And that is all. So these are the, and yes, of course, the velocity is uniform at each section. So with these assumptions, we start now writing the simplified version of our three equations, starting with mass conservation. So my m dot is the mass that is flowing through my control volume that I have defined. So I'll apply it at the two stations that I have some knowledge of, that is far downstream, which I call station 3 or station infinity, whatever you want to call. And the other station is the rotor itself, right at the rotor disk. So accordingly, I can write mass flow rate m dot equals to rho A infinity into W equals to rho A into Vi, because the mass has to remain constant throughout. So whatever mass is flowing through the disk should be the same mass which is coming out at the far downstream location in the slipstream. So here we are now defining some new variables, like of course rho is your density of air. Your A infinity is the area of slipstream in far downstream location. So this is the point where my slipstream has been fully developed, like I mentioned earlier. And Vi is the induced velocity, as you can see here. And yes, A is the rotor disk area, which is A equals to pi into r square, where r is my radius of the rotor. All right, so this is the information that we get from the mass conservation. So moving ahead. Now, if I apply the momentum conservation, so the equation comes out to be like this: minus F equals to T, where T is my thrust, and that is equal to the rate of change of momentum going across the control volume. So what is the momentum that is leaving the control volume? M dot W. And what is the momentum that is entering the control volume? M dot into 0. Right? So we have assumed that my control volume is to a point where my velocity is very, very small, it's close to 0. So there is no momentum as such entering the system, while the momentum leaving the system is m dot W. And this negative sign actually is because there is equal and opposite. So the work done by the rotor on the fluid would be opposite to what fluid is doing on the rotor, right? So by that argument, we get this equation. So now we have two equations. One is this mass flow equation, and second is the momentum conservation equation, which is thrust equals to m dot W, and W is my slipstream velocity. And finally, we come around to apply the energy conservation. So it's actually a power equation. So work done per unit time, which is equal to T into Vi. And so work done is, because that the force, that is what is actually being applied by the rotor on the air, and in that process the rotor is actually making the air go out with velocity v dot right at the rotor, or other W when it comes out far away. So the work done at the rotor is actually T into Vi, because that is the velocity which rotor is inducing into the incoming air. And the kinetic energy of the fluid that is changing is the kinetic energy leaving the system, half m dot W square, minus the kinetic energy which is entering the system. So half m dot V infinity square far upstream, and this part is again 0, okay, because we are considering it far up. So now in a nutshell, we are now left with these three key equations. And if I make use of these equations, I can actually now get some very useful information about my hovering rotor. Let us see how. So if I make use of the equation 2 and 3, and eliminate T between them, I would get the relationship V dot equals to half into W, or the W equals to twice of VI. What was my VI? Is the velocity induced by the rotor. So we call it induced velocity, and W is my slipstream velocity. So this is a useful relationship, W equal to twice VI. This actually also gives me another information that because if my mass conservation holds true, that is rho A VI equals to rho A, m dot is constant everywhere. So rho A VI equals to also rho A infinity W. Then my, so you can use A infinity everywhere or A3, whatever. I don't know. What did I use earlier? I guess I was using A3. Just one moment. Let me see. I am writing it A3. A infinity. Okay, I wrote A infinity there, and afterwards I'm writing A3. So just let's make everything A3. Sorry, A infinity rather. So this is A infinity, and this is A infinity. So what I get actually by doing this equivalence of conservation of mass and the fact that W equals to twice VI, I get this relationship A infinity equal to A by 2, or this radius R3, or rather R infinity, that is the radius of the cross section of the slipstream far downstream, is equal to the rotor radius divided by √2, which approximately is 0.71 R, or 71% of the actual rotor radius. So in far downstream region, my wake has shrunk to this kind of radius. So that is a nice, interesting theoretical result for me. But what is it there in reality? And it is not very difficult to measure this kind of wake for any rotor, and people have done that, I mean, in the past. And what did they find? So they found that this number, this radius, actually is not 71% of the radius, it's actually around 78% of the radius. So the experimentally measured quantity comes out to be 0.78 and not 0.707 or 0.71. So we see that this very, very simple model, where we have made some really, I would say, dramatic assumptions, which we know are not entirely true, still gives me an answer which is right there in the ballpark. So I don't know if you're familiar with this phrase called ballpark number. So when your answer is very close to the correct answer, we say it's in the same ballpark. It's an American phrase. So we are getting actually a fairly good ballpark number. I mean, I'm only off by almost 10%, not so bad. In helicopter world, a lot of times, I mean, simulations and the best and most sophisticated simulations around the world are off by 10 to 20%. Yeah. So we are used to of looking at that kind of numbers, because the whole aerodynamics is very, very challenging. So this is still fairly good for such a simple theory, which I can derive in a matter of minutes and understand it also in matter of minutes. So bottom line being, the slipstream area is half the rotor disk area. And if I now go back to the first equation again and find this new relation. So I use the same equation, T dot T equal to m dot W. M dot is rho A VI, and W we now know is twice of VI. So the entire thing becomes 2 rho A VI square. So this I can invert to get this expression where induced velocity is now written as P by 2 rho A. And this is a very, very useful information, even though it's coming from a very simple theory. I can also rewrite this as square root of 1 by 2 rho into a new parameter called DL, or disk loading. So disk loading is a similar parameter like what you have also in fixed wing world, which is called wing loading. So in fixed wing community, when I'm trying to design an aerial vehicle, we often talk about something called WL, which is lift or W per unit area. So W is your weight of the aircraft divided by the area of the wing. So A is wing area, total wing area. So that becomes wing loading, and it actually turns out to be a critical parameter in design of air vehicles. Exactly like that, in helicopter world, we have this disk loading, which is a very critical parameter when it comes to design and even analyzing or comparing different helicopters. and that's called disk loading, E by A. So now, because the same kind of induced velocity may be seen in future for climbing rotor, for descending rotor, for forward flight rotor, or maneuvering rotor, because rotor is inducing velocity in all flight conditions. So we differentiate that with the special case of hover. We also call this particular expression as VH. So my VH, that is hover induced velocity, is given by square root of T by 2 rho A. Okay. All right, so, and the unit for that is Newton per meter square in SI units. Sometimes people use kilogram per meter square, but Newton per meter square is more common. And in America or in FPS world, people were here, they are still using the imperial units. They denote it by pound per feet square. And let's see what are the typical numbers for these. So in SI units, you can see that this comes out to be from 250 to 600. Okay, so 250 to 600 Newton per meter square. And for FPS units, actually, because I got trained in US in this, so I am still inside my mind. I mean, I still can think of, okay, I mean, what are the numbers in FPS? So starts from 4 to 5 to 12 actually. Okay. So 5 to 12 is a common number. 4.5 is also quite okay, especially for smaller helicopters. So normally for larger helicopters, you will have higher disk loading, and smaller helicopters, you will have lower disk loading. So at this point now, I'd like to ask a question. So now we have seen that, okay, we have this induced velocity, which is the velocity which rotor will be inducing. And we also see that it is actually a function of this disk loading, or it is inversely proportional to the disk area and directly proportional to the amount of thrust that the rotor actually will be generating. So now if I want to design a search and rescue helicopter, okay, what would be the key parameter that you would want to control among the parameters we have seen so far? Yeah. So in other words, I mean, to make it more specific, my question is that if I want to design a search and rescue helicopter, a helicopter which is going to go and rescue people from, say, rivers, or somebody is stuck in an avalanche or something, in a snowy environment, you have to go and rescue that person, or from an ocean. So would you prefer, I mean, all things being constant, would you prefer a larger rotor, or would you prefer a smaller rotor, and why? Who wants to answer? You can raise your hand. Anybody?
Would it be a smaller?
You have to give me the answer also.
large,
Why you think smaller?
Yeah. A larger rotor, because then disk loading will be less, so the downwash will be less. It will be easier to pick things and move out.
So you are saying it should be larger rotor, or you are saying it should be a smaller rotor?
I don't know. There are two ways to look at it. One is the velocity inducing downward shouldn't be too high, because then you'd probably.
So to get the induced velocity smaller, you want a larger rotor or a smaller rotor?
To have smaller induced velocity, you should have a larger rotor.
Right. So you are saying the rotor should be larger.
Yeah.
Okay. Any other view other than Aditya's view?
I could give a counter argument myself, which would be smaller rotor would be easier to maneuver and move around and go into tighter places.
Okay. Okay. Fine. You are already thinking like a designer. Any other third view, or anybody wants to add or subtract from what he has said? I mean, hovering is necessary always. I mean, so I can hover with a larger rotor also, Gautam, and I can hover with a smaller rotor also. Question is, I mean, which one would I prefer? I mean, if I'm designing a rescue helicopter, which I actually did. I mean, in 2005, American Helicopter Selecting Design Competition, our goal was to design a mountain rescue helicopter with certain other requirements, of course. We are also winners of that particular competition. So no other comments? All right, fine. So the answer actually I mean, Aditya has made both the points quite apparent, that smaller rotor would allow you to operate from much narrower and smaller areas. True. But then, I mean, if I am going to rescue someone from water or something, I would prefer the downwash to be as low as possible. Yet, I cannot actually have a rotor of infinite radius, right? So the radius of the rotor will depend on what I can easily manufacture, what I can easily put on top of a helicopter. So finally, the disk loading will be the deciding factor. Okay. But yes, I mean, I cannot actually go for a disk loading too low because rotor may become too large, and that may not be perfect. But ideally, yes, the key driving parameter here is that I would want disk loading to be as low as possible within my permissible limits. So relatively larger rotor will be preferable, again, based on other constraints. All right, so that was my comment. So pretty much Aditya covered, I mean, what I was expecting. Right, so now we have got this formula for induced velocity, but so what? I mean, I need to know more. So what is that more? Now, with this, I actually can write the expression for power, which is far more useful for me. So VI we saw was square root of P by 2 rho A. And I know that power formula is T into VI. That is my power. And T into VH for hover, then it comes out to be T to the power 3 by 2 by square root of 2 rho A. So that's the power I get actually. And this power we call ideal power. Why ideal power? Because of the very, very strong assumptions that we made, which are not true for the real world. They are okay for an ideal world where there is no viscosity and things like that. So therefore, we call this ideal power. So how does this ideal power compare with the real power? Well, clearly, I mean, this is a function of thrust to the power 3 by 2. So if I plot it, I mean, I'll get a sort of a expression like this. Let me go slightly down. So I can draw this graph. Okay, let me draw this graph again separately because I would say this is slightly not well drawn. So power on the y-axis and thrust on the x-axis. So this graph you can see at t equal to 0 starts from here, and therefore it would go somewhat like this. That is my ideal power. P ideal. So what is the P real? How does that look like? So if I make some experimental measurements, I'll see them to be somewhat like that. So you can see there is a clear offset right here, and this offset also grows with the value of thrust. So this is what you will get from experiment. So what is the source of this difference? So easier thing to, of course, see is that the assumptions that we have made while coming to this ideal theory. And so again, I mean, this ideal theory is, we cannot say it is accurate, but it captures the trends the right way. In the sense, it is something which is sort of giving you an ideal lower limit of the kind of power my rotor would actually require for a real flight. So this becomes an ideal limit of minimum power that one can easily calculate on the back of a napkin paper. So it's a very simple formula. I mean, anytime I have to think about how much power I require, I can calculate this. But also beyond that, also there is another thing which we'll see soon, that is called figure of merit, which will allow you to convert this ideal power into a real value. So now, before we continue further and define the figure of merit, I'll quickly define few non-dimensional parameters and quantities. because that would be needed when I want to write the figure of merit, because figure of merit itself is a non-dimensional efficiency factor. Because now, after we have reached this point where we now know, based on this very simple theory, that I can calculate the power required by a rotor to generate a given amount of thrust. And this thrust, if my helicopter is in hovering flight, is going to be equal to weight. So that way I can know the power required for lifting off. And it's true not just for helicopter, I can do the same for a quad rotor, right? So imagine a quad rotor. Right, so this is my quad rotor. I mean, badly drawn, but still looks like a quad rotor. I can use the same exact expressions to find out the performance of this quad rotor also, like how much power my each motor would be requiring. But that will be ideal still. And how do I convert it to real? We'll come to that. So let us see some non-dimensional parameters. Now, what happens? I mean, the more fundamental question is that why do we non-dimensionalize things? What is the reason for that? Who wants to answer this question? Why do we do non-dimensionalization in engineering, not just in helicopter world, but in all engineering? I mean, whether it is aerospace, whether it is
get rid of system of units, maybe, like it would be same irrespective of system of units we are using.
Yes, units, but so you are saying that, I mean, right now the numbers would be dependent on the units, right? That's what you are saying.
Yes, sir.
Fine, that is a valid argument. What else? Information exchange become easier. That's Gautam is saying it will be independent of length. Yes. So very important point which Naveen is making is it becomes independent of our physical dimensions. So imagine, I mean, somebody asks you to compare a small helicopter's performance with a large helicopter's performance. Okay? And it tells you that, okay, this guy is generating some 10 kgs of thrust, the other guy is generating 1000 kgs of thrust. Now, I mean, you will be feeling lost how I make a comparison. I mean, one guy is at 10 kilograms, other guy is at 1000 kilograms or some very large number. So that's why, I mean, if I make it non-dimensional, the physical dimensions and numbers do not now, I mean, affect my scale of things in some sense. Yeah. So it becomes easier actually to then make apples to apples comparison once I talk in the once we go into the realm of non-dimensional parameters. And that's why we talk about Mach number, right? We don't talk about speed of sound or speed of other things, because now, I mean, with this non-dimensional parameter Mach number, I know when the supersonic or when the compressibility effects become important. So I don't have to remember the number, speed of sound and different media and so on at any point of time. Reynolds number, another non-dimensional parameter which actually gives you the extent of, I mean, the level of turbulence in flow, whether the flow will be laminar or it will be non-laminar, and such information like that. So now for a helicopter world, what we do, we divide all the parameters that has length scales by radius, which is, the symbol is capital R. Symbol is omega, capital omega for your rotational speed in radians per second. So we divide all the velocity terms by omega into R, which is the tip speed. And tip speed is also important design parameter because it controls the Mach number and your other scenarios. So now we define, so you saw thrust earlier, which was dimensional thrust, and we saw power earlier. So we'll define now non-dimensional parameters, just thrust coefficient Ct, which is T by rho A omega R whole square. And for a helicopter, in hovering condition, this thrust coefficient would typically vary from 0.004 to 0.014. And a moderately loaded helicopter would be hovering at, say, 0.006 or 0.007 or thereabout. Yeah. So this is a moderately loaded helicopter. That is, I am in the midway. Because what happens, I mean, if I load it heavily, my blade may require higher pitch angle and it may go close to stall and so on. But this is a moderate scenario. Be it a small helicopter, be it a large helicopter, if I compare them at same level of CT, I can expect that they would be operating under similar condition to a certain extent. Then we have power coefficient Cp, which is P by rho A omega R whole cube. And yes, this thrust coefficient and power coefficient are also encountered in propeller theory, but there the definitions are slightly different. You don't use the same expressions like these. But the idea is same to make it non-dimensional, but formulas are different. So be careful when you encounter those in the propeller theory, which we normally taught in flight mechanics course. So now power coefficient is defined as P by rho A omega R whole cube. Apart from thrust and power, another important parameter of great interest is the torque. So torque, of course, I mean, has multiple implications. One is, I mean, power will tell you that, okay, what kind of engine I'm going to select for my helicopter. How do I select that, right? So if I know the power, I know, okay, this is the power I require for hover. So I must keep some factor for other auxiliary equipment, for other losses and other motions, maneuvers, etc. And then I'll choose some power plant based on that. But torque, the torque tells you that how I design my rotor shaft, the helicopter shaft which is supporting my rotor, how I design my transmission, because mostly engines will be operating at very high RPMs. My rotor may be spinning at much lower RPM, and the rotor may require very high torque. My engine may not be able to deliver that kind of torque directly. So therefore, you require some kind of transmission in between, which will allow you to scale the torque. The engine torque will be increased, and the engine RPM will be decreased in the process. Because what happens, the simple formula for power transmission. So we'll use some kind of mechanical transmission to transfer the power. So at one end, if my torque required is, Q1. So torque we denote by Q, not by T. Okay, so that's the symbol Q. So we have Q1 and my angular speed is omega 1. So this could be the torque required by the rotor. So I can say Q1 and omega 1 is the speed of the rotor. And at the engine end, so I can maybe say QR for rotor and omega R for rotor. And I can say QE for engine and omega E for the engine. So the power has to remain same beyond certain losses. So this is how it will scale up. So you can see my omega of the rotor is smaller, omega of the engine is larger. So I step it down by using a transmission, which will slow the rotor down. And in that process, I will actually be scaling up the torque. So if I use a nice mechanical transmission, a system of gears, planetary gears, spur gears, bevel gears, all whatever is required, you would actually end up getting a scenario like this. All right. So therefore, the torque actually becomes important as well, other than the power. So my torque coefficient is defined as Q. Now it's Q into omega. So from the same formula, I can extract, and the torque coefficient itself is defined by this Q divided by rho A omega R whole square into R. So now we see if I multiply this with omega up and down, my non-dimensional torque coefficient and non-dimensional power coefficient are exactly identical. And the typical order for this is 10 to the power minus 4. So here we are having 10 to the power minus 3. The power coefficient is an order of magnitude smaller, 10 to the power minus 4. So it will be like 3 into 10 to the power minus 4 or 5 into 10 to the power minus 4 or something like that. So these are the key definitions. So now we go back to the induced velocity and right. So we go back to the induced velocity and non-dimensionalize it again. Okay. So we divide this by omega R and we get this new parameter called inflow. And this lambda h we call as hover induced inflow ratio. So this is called inflow ratio. So the dimensional velocity was called induced velocity, And once you divide it by omega into capital R, it becomes inflow ratio. Sorry, there's no N here, the inflow ratio. Right. And typical number for this is 0.03 to 0.08. Okay. So you can get an idea that compared to the tip speed, the velocity which I am inducing is so small. So what is the velocity? I mean, at the tip, it's around 0.65 Mach number. So into 330 meters per second. So which would be roughly 220 meters per second or something. And 220 meters per second, you further divide. So it will be 6.6 meters per second to, I'm just doing very crude calculations here. Okay. Maybe 13 meters per second or something. So that is the kind of range you will actually get for induced velocity. These are the typical numbers for a typical helicopter. Now numbers can increase, decrease depending on the size and other things. But that's the kind of number I mean to give you a feel, because it's very, very important. Being an engineer, it's absolutely critical to be aware of the numbers you are dealing with. You must have a feel for those numbers. You cannot blindly do things. Also, it is completely wrong to write numbers in unnecessary decimal places, because you are used to using calculators, and calculator will, if you do a calculation, it will throw out numbers like 2.3419 something, okay, some really long number. But if it is a dimension of say a radius of a rotor, you will simply say 2.3 meters, because you are not going to measure the or try to achieve the accuracy in millimeter level, right, for a rotor of several meters radius. So be careful about numbers, units, and dimensions, and give them good respect. It's very, very important for an engineer. All right, so now I go back to this equation and see V by omega R. I push that omega R inside the formula, and wow, okay. Now I have a really nice, simple, elegant formula to remember that over induced velocity lambda h is square root of Ct by 2. So you can note down this entire expression. It is simple, straightforward. Same lambda I equal to lambda h Vi by omega R, and omega R now pushed inside. T by 2 rho is already for Vi, and that gives me Ct by 2. So now my Hoover induced velocity, or sorry, Hoover inflow ratio. This is Hoover inflow ratio. Hoover inflow ratio is Ct square root of Ct by 2. And likewise, power. I can do the exact same thing for power, convert it into the non-dimensional form. So T to the power 3 by 2 rho A is my power, which is T into VH. And I can now directly jump to the definition of Cp being equal to P divided by rho A, and sorry, what am I doing? Saying, yeah, rho A into omega R whole cube, right? So I just jump into that, put the value of P, and reorganize things up, and I get this new expression now. So Cp equal to Ct to the power 3 by 2 divided by root 2, or you can write this also as Ct into lambda h, where lambda h is Hoover induced inflow, and Ct is my thrust coefficient for hovering flight, which is also, so sometimes we also use the symbol Cw equal to Ct for Hoover. Okay. So that is the expression I wanted to get. So now we'll look at another definition. So we saw disk loading earlier, T by A. Now we define a new parameter called power loading, and that is T by P, that is thrust per unit of power. So by looking at this itself, you can immediately make out that this actually is a measure of efficiency for a hovering rotor. How is that? Because it is telling you that with every unit of expenditure of power, how much of thrust can I generate, right? Thrust per unit power. So I take a rotor and it generates, say, 1 kilogram of thrust with an expenditure of, say, 50 watts of power. So now 1 kilogram per unit divided by 1 divided by 50 watts of power, right? 1 kilogram. So I can write this as 9.8 newtons by 50 watts. So I can write this as something in newtons per watt, or I can even write it in kilogram per watt, whichever way you want. Sometimes people write it kilogram per watt or newton per watt. But when I deal with bigger helicopters, then what happens? This number becomes kilowatt, becomes very large compared to the overall thrust. So then people indicate it in terms of newtons per kilowatt, like this, as you see here. Or you talk in terms of pounds per HP, and that is your power loading. That is thrust per unit of power. And this turns out to be a measure of hovering efficiency. Okay. So if I write P equal to T into VI, VI equal to P by T. So we can see that my induced velocity is inversely proportional to power loading. That is a very useful information. And yes, the question that I forgot to ask is that based on this definition of power loading, what do you want? If I want to make my helicopter more efficient or my rotor more efficient, do you want a higher power loading or do you want a lower power loading? Which is more higher? Anybody else? Everybody agrees that we want higher power loading?
Yes, sir.
Yes, no, I don't know. Speak up or use chat box. Okay, yes, one yes. Right. So however higher, we want this to be eventually higher, as high as possible. Higher is better because that means that, I mean, for every watt of power spent, I am actually able to lift more weight. That's what you want. You want to be able to lift more and more for every ounce of or every watt of power that you end up spending. So this becomes a measure of hovering efficiency. And we see it's inversely proportional to my induced velocity. So my power loading is equal to 1 by VI, based on ideal things, not necessarily in the real world. But as we see that my induced velocity and all these parameters are actually physically consistent, they may not be very, very accurate, but they give you right indications. So power loading is sort of inversely proportional to induced velocity. What does this tell you? A larger rotor is more efficient or a smaller rotor is more efficient? All things remaining same.
Larger.
Larger is more efficient. All of you can see that? Perfect. Yeah. So therefore, that's why I mean, see, the larger rotor actually gives you other advantages. I mean, I end up reducing my induced velocity. I end up improving my efficiency in hover. But that doesn't mean that, I mean, I'll go for a very, 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 very large rotor actually all the time. Why? Because the same large rotor will actually become more draggy when I go in forward flight. Because a helicopter also has to do a lot of forward flight to go to the mission area, to do various operations. And therefore, you have to come up with a compromise that, okay, how big my rotor should be so that I have adequate hovering efficiency and also adequate forward flight capability. Right. So this or otherwise, I mean, it becomes inversely proportional to square root of disk loading. So therefore, to maximize power loading or minimize power required to produce a given amount of thrust, we must have a low value of induced velocity, or we must have a low value of disk loading. And therefore, to have a lower disk loading, that means I must prefer a larger disk area or longer blades. But longer blades also have higher weight because they are longer. They will also need to be stronger because they will become slender. And a lot of other things also come in, apart from the drag you encounter in forward flight. Therefore, you have to draw a line somewhere. You have to come up with some compromise which will give you what you want. So take this down, that to maximize power loading or improve the efficiency, we must go for a low value of induced velocity and low value of disk loading. To get a low value of disk loading, I must have a larger disk area or longer blades. So keep that in mind. Normally, and that is why. So now you can imagine people often ask me this question, okay, and now you will be able to answer that also. They ask me, okay, so there are these, multi-rotors there, okay, which has 4 rotors, right, connected like this, okay, and then you have a helicopter which has single main rotor and a smaller tail rotor. This rotor may be larger compared to the small 4 rotors. So which is more efficient? Is the helicopter more efficient or the quad rotor going to be more efficient? So now you can see clearly that larger rotor is there in helicopter. So aerodynamically, my helicopter configuration of similar weight class would be more efficient compared to this quad rotor, which has smaller rotors and smaller propellers. So purely on aerodynamics, helicopter wins. Okay, so now I'll directly jump from here to this figure of merit. So now we define one parameter for efficiency, that was this loading, right? So power loading. Yeah. But then power loading, as we saw, was newtons per watt. It was kilograms per watt. So it's a dimensional parameter, and therefore it is not very convenient. If I compare different rotors, I cannot actually compare them carefully because they are dimensional parameters. It is fine to analyze one rotor. So if I give you one rotor and say, make these changes, change the airfoil, change the cord a little bit, make some minor modifications here and there, and check which is more efficient. In that case, power loading could be good. But if I have to compare 2 other independent rotors of different weight class, sizes, and so on, then a better parameter actually is what we call the figure of merit. So as the name suggests, it gives you a number which checks for the merit of the rotor in hover. The figure of merit can be used as a measure of hovering rotor efficiency or efficiency of a hovering rotor. If we had perfect rotor, figure of merit would have been 1. So if you had an ideal rotor, the figure of merit will go to 1. And the definition of figure of merit, as you can see, is ideal power to hover, that is momentum theory power, what we derived in a moment back. And divided by actual power to hover. Right. So that's what it is. And so it's like an efficiency parameter. Okay. So in most systems, you have some kind of efficiency parameter. So this is an efficiency parameter for a helicopter. And that's how it is defined: ideal power by actual power or real power. So actual power is, I can also call it as a real power. That is what you actually measure experimentally, not by any theory, or by a very accurate theory, one can say. Okay. So now ideal power here is given by momentum theory analysis, which we already know, that is P equal to P to the power 3/2 divided by square root of 2 rho A. But then what happens to this actual power? How do I get this actual power? So a while back, I made a graph. I showed you a graph which actually had this experimental measured power. So let us look at that again. And that is how this graph comes out. So if you had drawn that earlier, you can redraw it now, because here now things are more information is given. So this blue line here, which you see clearly, is the ideal power, which is varying with so this guy is varying so this is varying with Ct to the power 3/2. All right. And the real power, which is here experimental, this actually has one offset, which we call as the Cp naught. So this guy we call Cpi, which is actually the induced power. This power is purely because of the velocity that the rotor is inducing. But when in real world, even when the rotor is not generating any power, there is still, it's not generating any thrust. The rotor actually ends up consuming still some amount of power. So the question is, what is this power? This is called profile power. And what is the source of this profile power? Who can tell me? What is causing this profile power when I am not even generating any thrust? Anyone? They're still there, right? Drag, yes. Absolutely. So when you get lift, you also get drag. I mean, in momentum theory, did we talk about any drag? We did not. Right. But then, I mean, you have seen the airfoil, you have seen the wings. If there is lift, there will be a drag. And ideal theory, because in that there was no concept of a blade, there was no concept of a rotor. We only had a disc. So we got only things through momentum, and momentum doesn't, because we looked at conservation laws. When there is drag, your conservation laws are no longer valid. So it doesn't account for the drag. And therefore, we have this, what we call profile power, which is due to the drag that rotor is experiencing. So that is the one part. But when we go further up, okay, this is what is there, but this gap. So if I translate this particular line, the ideal line, to this, I add. So this line is Cp ideal plus this Cp naught. If I do that, it actually comes out here. And there is still a difference between what is there in the experiment and what is there by adding Cp ideal plus Cp naught. So what is the source of this additional difference?
Swirl.
Sorry, Aditya, what did you say?
Is it swirl?
Yes, one part is swirl, yes. Other part could be compressibility effects to some extent. Another part could be the tip vortex, which we conveniently ignored. So all these other losses coming from the overall swirl in the flow, the presence of tip vortex, or some minor compressibility effects and overall viscosity effects. So all those things combine together and cause further losses, which we have not accounted for. And it turns out that if I actually multiply it with a small factor here, which we call induced power factor, we end up getting better correlation. So this graph then will actually change. Let me change the color here. Yeah. So then this graph would actually tend to follow this line somewhat better. Okay. So it will be somewhat close to that. May not be 100% exact, but it will be fairly close to that. And that's why that is how I actually get my total power. So the total power now has Cp naught plus this kappa. So this is kappa not K times Ct to the power 3 by 2 by root 2 in the non-dimensional form. Right? Because this is my non-dimensional power. This, when I write as Cp, it becomes Ct to the power 3 by 2 divided by root 2. All right. So that's what it is. And but I don't know what is the Cp naught. So let me quickly wrap it up because we are only anyhow out of time. So this kappa now you can define and write that it is called induced power factor, which accounts for all non-ideal effects on induced power. The typical value of kappa in hovering flight is taken as 1.15. Note this down. Typical number. If nobody says anything, you just blindly take this. And Cp naught, the profile power coefficient is obtained using an advanced theory called blade element theory. We will not cover this theory in this current course. We teach this in the helicopter course. So what does blade element theory give me? It gives me Cp naught to be equal to a new parameter called sigma CD naught by 8. What is CD naught? All of you are familiar with this already.
Drag coefficient.
Not just drag coefficient, but CD is drag coefficient. CD naught actually is the zero lift drag coefficient. That is, normally your drag coefficient of an airfoil will be function of your lift or function of angle of attack. But when I put this angle of attack at a point where my airfoil will have zero lift, okay, then that drag coefficient is called this CD naught, the zero lift drag coefficient. And sigma is a new parameter called solidity. Okay. So it's already 1:05, so I'll stop now. Okay, I'll define solidity in next class, and we'll just quickly take a recap of this, and then we'll complete we'll solve one example. Okay, we'll solve one simple example. Okay, for yes, so I'll complete the definition of figure of merit with this, and we'll solve one example, and we'll then finish off the part on helicopters. All right, and well, we guys told you about the term paper long ago, did we not? If you are sitting up to now, okay, no, I won't be uploading this PDF. I mean, you know, this PDF won't be uploaded. I mean, you have to take notes when you are attending a class. Okay, so I won't be uploading this PDF, and that's why I was skipping it through it very carefully. I'll upload the recording, and if you have not taken notes, you can take notes from there. Question of the deadline was discussed long back. Okay? The deadline is not discussed now, right? So if you have been sitting and not working on it, I mean, that's not our fault. I'll talk to Professor Das and we'll see whether we want to increase the deadline or not.
Do you have a list? Who is doing what term paper? That should be with us first.
Yeah. That list, I mean, has not been mailed to us actually. Okay, so who is doing what? The mapping has not been shared. Individuals have asked about certain topics, but that's all. We don't know the full list of who is doing what.
I think we should receive now from everybody, and then we should have decided a date.
Right. So you share that. I mean, where I mean everybody's thing is done. Okay, we know who is doing what, and I'll discuss with Professor Das, and we'll announce it by next class. Okay.
Sir, I put the link of the sheet in the chat.
Can you send it by email? Okay, because
Okay, sir, I will send
okay,
it.
just send the email in the course list. AE 201A. Okay.
Okay, sir.
Yeah. So that it will be there with everybody. All right. Okay. So thank you, and I'll see you guys next class.